So, good morning, or good afternoon, or good evening to everyone. I'm Betty Du Bois, and I'm here with Mike Kershaw. And I just want to let everybody know before we start that if you have any questions, just go ahead and put them into the Q&A section, and we'll be watching those. And if you see a question you absolutely love, be sure to go ahead and do a thumbs up on it and click those up, because I'm thinking Mike might answer those first. So go ahead and take it away, Mike.
All right. Hello, everyone, and welcome to the Kismet and Wireless Security presentation. So I'm the author of the Kismet Wi-Fi tool and a bunch of other Wi-Fi related tools. I've been involved in Wi-Fi security since 2001 or 2002. Kismet is over 18 years old now, so software that's old enough to vote means get off my lawn. But why do we care about this? I mean, Wi-Fi sniffing's been around since the late 90s. The first 802.11 stuff started launching around 1999. Wi-Fi is still only becoming more and more prevalent. The majority of corporate deployments are Wi-Fi now. They still do Ethernet to some desks, but I think the number of companies that do Wi-Fi based laptops and everything far outweighs that. There's also Wi-Fi for sensors and control networks, etc. So yeah, everything's moving away from wired. So why is wireless special? I mean, why do we need to have a special talk about it and special software? Can't we just capture from it like we can with everything else? Aren't there enough tools that monitor packets out there already? If only had a conference about some of those tools. But Wi-Fi is a bit of a unicorn. It's a bit special. It is truly shared media. Every transmission impacts someone. You're not just limited to your physical network like you are with Ethernet. So on like a hubbed Ethernet, everyone on the same physical network interacts with each other. But with Wi-Fi, every adjacent network or adjacent device, even if it's not part of your network, impacts the performance and integrity of your networks. It isn't Ethernet. Your OS might present it like it's Ethernet, but it isn't. Knowing that a network is present based on advertisements that the network is around isn't the same as knowing what's really going on with it. So you can know that you have 10 networks near you, but you don't know that they're heavily in use, if they're idle, etc. If anyone remembers their OSI model, the 7-layer model, you're going to really care about layers 1 and 2 all of a sudden. Most of the Wi-Fi issues and issues with capturing happen down on layer 1 and 2, the physical and data link. So if you want to discover Wi-Fi networks, there's several ways to detect them. The traditional way would be scanning mode, where it detects it based on advertisements. So the network beacons out, I'm a network, here's my name, here's my encryption options. You can detect those. That's how your operating system finds the list of networks near you, but it's not packet capture. It won't show you things like clients, it won't show you data traffic going on, and it won't show you problems that are happening on the network in that regard. Similarly, some enterprise access points have assisted capture, where they can discover APs near them. So you can do, find interfering APs and automatically list APs and pick channels. That's still looking for advertising access points, not capturing the packets. We want to see what's actually in those packets. So how do we get them? We can open the Wireshark, we can open the Wi-Fi interface in Wireshark normally. You'll get some sort of packets out of it. So, if you just do a capture from your Wi-Fi interface in Wireshark, you'll get something that looks like this. Wait a minute. Yep. So we don't want that. The OS is presenting the Wi-Fi card as a traditional Ethernet device. That's because the operating system and the rest of the stuff on the network stack on your system know how to work with an Ethernet card. The data packets on Wi-Fi can hold the same content as Ethernet, so this makes sense. But this capture will only get as data packets, usually only from your single session, possibly broadcast depending on your driver, or it's a little random what happens. There's a lot more to Wi-Fi than just the data packets though. And there's even more to Wi-Fi data packets than just the data you get in them by capturing in this mode. So what we really want is something where we get the full Wi-Fi packet, where here we can get the signaling header, radio information, low-level control information, and then after all of this comes the data packet that was all we could get before. So how do we get to that? With traditional network cards, there's promiscuous mode. It just turns off the packet filter and you get all the packets. So you still get, but they're all Ethernet packets. For Wi-Fi, we need a whole other mode of operation. So Wi-Fi calls that monitor mode or RF-MON. The operating system won't understand what's coming in anymore because it's going to be raw 802.11 or 802.11 with signaling headers. But Kismet and Wireshark and other tools like that do understand it. Monitor mode isn't part of the official spec, but lots of drivers support it. Unfortunately, there's a bunch of exceptions in strange behavior because of course there is. Why would this be simple? So the fun part, we need an operating system that supports monitor mode. We need a Wi-Fi card with firmware that supports monitor mode. We need drivers that support the monitor mode for that card. That's a lot of moving pieces. You might think that sounds a bit intimidating for getting the right stuff, and you're right, it can be a real hassle. It means the specific chipset of the card matters. The brand doesn't necessarily matter. The model doesn't necessarily matter. A lot of manufacturers, especially of consumer gear, will change what's inside the card without changing the product name. They won't change the model. So like a TrendNet 111 has 3 different revisions with 3 completely different Wi-Fi chipsets inside of it. And what we care about is the actual chipset that's in there. So you need to do additional research to find out exactly what's in it. And it often means buying from companies that advertise what chipset's in their card. Other problems with monitor mode is it is not a standard, so it's not required. It may not be consistently implemented. It might not be implemented at all. The common failure modes for it, you might think you're going into monitor mode, you just get no packets. You might get only data packets and none of the other types. Your packets might be corrupt, you might get bogus packets. It's easier to get into monitor mode now than it was 10 years ago or so, but it still's got its challenges. Kismet tries to solve this automatically whenever possible. So in general, Kismet, if it can detect your cards, will bring them up into the correct mode and configure everything already for you. So we said one of the problems is missing the firmware modes for monitor mode. This happens a lot on mobile chipsets. Unfortunately, mobile chipsets are also found on things like the Raspberry Pi. So as shipped from Broadcom, the drivers for the Pi do not have monitor mode implemented in the firmware. There's some projects to replace missing monitor mode firmware. So Nexmon solves it for Broadcom, where they actually reverse engineered it and reinserted monitor mode instructions into the firmware for the card. With bogus packets, Wi-Fi packets will have a checksum, and you'd think that would be enough to solve this. So since Wi-Fi goes over the air and there's a lot more chances for interference, it's heavily checksummed in ways that Ethernet isn't always. So you'd think that would be enough to solve this problem, but some drivers just don't report the checksums at all. They're just not included for no good reason. So we have nothing to validate against. Some only report that the checksum was valid. They don't give you the checksum data. They just say, we think this packet was valid. So if the driver implements that check incorrectly, there's no way to compare the data for your own purposes to find out if you're getting valid packets. And some packets report a checksum, or some drivers report a checksum, but they calculate that checksum from the data in the buffer, which means it has no relationship with the actual packet. It's just, sure, we checksummed whatever random garbage we got, so it's okay. So that defeats the entire purpose. To complicate things even further, Wi-Fi keeps evolving. So, 802.11b, G, A, N, and then we ran out of letters. So there's AC, AX, and so on. Each iteration of the drivers have significant differences and challenges, both in what kind of packets are transmitted, the physical way packets are transmitted, et cetera. And generally, the newer and faster the Wi-Fi standard is, the harder it is to capture because it's got more information going at a higher data rate, which means the effective signal level is lower. And it means that the encodings are often more challenging to receive. So can you see everything out there? You can't. As a passive observer, it's impossible to get guaranteed total coverage of a channel. Unlike Wi-Fi, you can't just plug into a span, or unlike Ethernet, you can't just plug into a span port and get every packet on the network. Clients and access points may see packets that you never will. And because you're a passive observer, you can't say, I didn't see that packet retransmit it. It's just, you won't see it. Compounding that is there are many channels. There's localized interference. So it might be traffic on a different channel than the one you're looking at, or there might be, Bluetooth or a microwave oven or something that disrupts the signal near you so that you miss packets, but the rest of the network continues to operate with them. So ultimately, you just have to accept that when you're monitoring Wi-Fi, you will not have 100% coverage the way you might with traditional Ethernet. So sniffing the older stuff, 11B and G and 11A, they're the oldest of the common Wi-Fi standards. There was some pre-11B stuff, but it wasn't widely sold or deployed. These are fairly easy to sniff. They're simple encodings, they're slow data rates. So it's easy to get the symbols, and it's easy to hear them because they're effectively speaking, loudly and slowly. It's one antenna transmitting. If you remember the old WRT54 access points, or if you picture a traditional access point in your head, you'll have the two little Wi-Fi antennas sticking up out of it. Even if you've got the two, only one of those is active. The second one is to help receive packets better. So there's only one transmitter. If you're in range, you're pretty much going to see those packets, but it's really uncommon to find legacy 802.11b now. More modern Wi-Fi, 11N, AC, and AX, use a technology called MIMO, multiple in, multiple out. What that really means is that you have, if you have 3 antennas, then you have 3 systems coordinating transmission and reception at the same time by doing all sorts of neat radio encoding tricks to effectively create multiple streams of data that recombine to form the packet. This means more bandwidth. This is one of the main reasons that modern Wi-Fi is so much faster. It means better resilience to interference, which is also why Wi-Fi is much more reliable now than it used to be. But because now you have multiple streams of data going out, bouncing off things, coming back and recombining, it's much harder to sniff because where you're physically located suddenly impacts whether or not you see the packet. So the client the packet is meant for might see it perfectly fine because it's bouncing off a filing cabinet and a wall, and the two streams are combining fine. But if you're 20 feet away, you might not see that packet happen at all because you missed part of the stream, and the network will never retransmit it because the proper receiver has already gone and acknowledged it. So it can be much more challenging to sniff data packets from the newer networks. And now with 11AC and AX, there's beam forming, which is next level sci-fi tech, where multiple antennas that would operate in any direction create a signal out of phase so that each antenna sort of creates the signal in sequence, and it effectively makes it a directional antenna out of multiple non-directional antennas. It means the access point can effectively aim the signal at a user, which increases the signal quality and the bandwidth and decreases the interference to other users. But it's terrible for sniffing data because now if you're not part of that beam, you're even less likely to see enough of the packet to be able to decode it. Also, sniffing the newer protocols requires the newer hardware. It's sort of an obvious statement, but you might see the beacons in the advertisements saying, here's a network, it's 11AC. For backwards compatibility, those are sent at a more common data rate where older cards can still see them. But so you'll see that the network is present, but you'll never see what's happening on it if you don't have a card that's of the same standard. So you'll see that 11N network exists, but you won't see its data with an 11G card. Similarly, you might see that an 802.11ac network exists with an 11N card, but you won't be able to see what's going on in it. So the newer Wi-Fi standards are much more complex, which means they cost more to develop. The licensing is more restrictive because more patents are involved now, which means there's fewer companies making it. So we went from probably 20 different varieties of 802.11b card and G cards that could sniff to just a handful of 11AC cards that can sniff, 3 or 4 at most. And as far as I know, there's one single 802.11ax card, the Intel AX200, which is capable of doing monitor mode. So what are the options that we have for capture? It really depends on your operating system. For OS X, you can capture with the built-in airport. So you can capture up to 802.11ac, and I don't believe there's an AX one yet, but I would assume that when there is, it will probably also work. Nothing else on the Mac can capture raw packets. There's no generic USB monitor capability due to a lack of drivers on OS X. So you can't buy like an 11AC USB card, plug it in, and have it work. And Apple is continually making it harder to add out-of-kernel drivers, unfortunately. Catalina has greatly restricted this, and I believe Big Sur is going to restrict it even further. Good for security, bad for adding capability like this for OS X. For Windows, Case made the ARP cap, but I believe that's been end-of-lifed. There are some commercial capture products. You might think, well, there's WSL, Windows Subsystem for Linux. Unfortunately, that can't talk to USB. There's WSL2, but that's based on Hyper-V, which is Microsoft's virtualization layer, which doesn't have USB support. So there's no way to actually interface to the hardware. Sometimes if you're on Windows, you can use a VM and run it in there, but we'll talk more about that. Linux is by far your best chance. Many chipsets work in Linux. I would even say probably most chipsets work in Linux. Of them, Intel, so the IWL Wi-Fi stuff found in most laptops works quite well with the modern kernels. There is a chipset from MediaTek, the MT76X2, has been added in recent kernels. It started showing up around the release of the 5 kernel, and it works really well. It does 11AC, it's USB, it's probably the best so far to get working. Older Atheros cards, the Ath9K 11N, work great. Raspberry Pi with patches, you can use the built-in cards. So you can use small embedded systems for capture and feed those packets elsewhere. You could also use a live CD if you have a laptop that's running Windows and you don't want to install Linux fully onto your hard drive. Cards to avoid, there's a chipset called the 8812, and it's found in hundreds of different brands of cards. It's very cheap, you know, $5, $10 cheap. It's unfortunately also very bad. The drivers are not, probably never will be in the kernel. They're always going to be out of the kernel because they're so bad and non-standard that they're effectively unmergeable. They tend to work or not work on any given Git commit, so it's almost impossible to reliably get them. So if compiling your own kernel drivers and debugging them isn't for you, avoid this chipset. And you can find out what chipset's in the card usually by the manufacturer page or with Google. Similarly, the modern Atheros Ath10K, which is a higher end 11N or 802.11ac card, has buggy firmware that reports just floods of bogus packets. And because the firmware is closed source, there are no fixes available for it. So if you wanted to try Linux, many distributions have a live version. So, you know, live CD, live USB that can boot without modifying the hard drive. Some are directly built around this. So Kali and Pen2 are good examples of distributions meant to run without modifying your hard drive. You can install them normally, or you could just run them off USB. And it's typically a quick way to get going, but it might not have the most current versions of the tools. And depending on how your laptop's configured, you might have to disable secure boot to be able to boot a system off USB, and that might interfere with your Windows file encryption. So just be aware of that when you go into it. Virtual machines sometimes work, but they're generally discouraged because they can be really funny. USB devices may work via USB pass-through. Wi-Fi cards typically do. Other cards often don't because of how the Windows USB driver model is written. It's very strange. If you have a PCIe or a PCI card like the Intels or the Atheros, they will not work because there's no way to pass that to the virtual machine. So if you're going to try it, your only chance will be with USB, and it might be a little flaky. I've seen success with VMware on Windows. I've heard that VirtualBox can work. Both of them on OS X tend to have problems, and often the community will refuse to help people with VMs because of prevalence of issues. So I've seen them work, you can get them working, I've helped people get them working, but if you, for example, like go to the Kali or Pen2 people and say that you want to run it in a VM, they probably won't be very receptive because there's so many problems with it. Your other option though is remote capture. So Kismet can support capturing from a Linux box over TCP. So any supported device, so you know a Raspberry Pi or a little OpenWRT router running the remote capture code for Kismet can feed packets to OS X or Windows. So you can effectively use a little Ethernet connected device and use that to capture packets when you couldn't connect to a USB device. So when is it worth all this hassle, since we've just spent 15 minutes talking about how it's inconsistent and a pain and tricky to find? You don't need to worry about this if you're looking at, say, analyzing data traffic from your own laptop. So if you're trying to debug at the application layer, if you're trying to debug HTTP or an application traffic, things like that, that's just data on Ethernet. So you can just capture it from Wireshark like you would normally. If you're looking at broadcast and multicast on your network, MDNS and whatnot, that should typically be capturable without monitor mode. Just open your interface in Wireshark. If you're able to capture network wide at the switch, so if you're hitting like a span port and you're grabbing all of the user traffic from your Wi-Fi network, you don't need to worry about the Wi-Fi packets, you just care about the user traffic, you don't need to worry about any of this. However, you absolutely do need monitor mode if you want to capture the Wi-Fi layer. So if you want to see hidden access points or deep information about the access points, if you want to see clients and what the clients are doing and what they're sending, in addition to what data is actually crossing your network, you can look for that. So if you want to see, clients doing peer-to-peer traffic like Wi-Fi Direct, phones can share Wi-Fi packets between each other without talking to your network at all. So that's a path of communication that your main IDS or capturing off your network side of things wouldn't see. If you want to monitor for people attacking your network or some denial of service conditions, or if you want to audit or attack WEP, WPA, WPS, other standards like that, you need the raw Wi-Fi packets. So you need to care about all of the minutia of getting the right interfaces going. So some of what Kismet does. So Kismet's designed to do several things in the Wi-Fi space. So it's designed to manage the different cards. It'll handle all the supported card types on all the supported operating systems. So primarily OS X and Linux. It'll run in WSL, but WSL is really just Linux, so doesn't really count. It'll deal with the quirks of getting them in a monitor mode automatically. There's a couple hundred lines of code that just match different drivers and try to accommodate their weird quirks. It'll keep the operating system from breaking the setup. Network Manager in Linux really likes to take over the Wi-Fi configs, even when you have it set up in monitor mode, and then reset your configs all of a sudden for you. So Kismet will automatically stop that from happening. And it will deal with handling all the different channels. So Kismet was designed to basically enumerate the network devices, access points, clients, and devices and their relationships between them. So it's more network and device centric than it is packet centric. For all the other functionality, it can talk to any other tools like Wireshark that handle packets. So it'll generate, PCAP, PCAP-NG, various different radio headers on the packets. So Kismet's been around since around 2001. And you might be used to it looking like this, especially since a lot of distributions don't update that often. So this is how Kismet used to look. Since then, Kismet's had a really significant rewrite. It's now got a web-based UI. There's REST and API and JSON endpoints integrated in, so you can pull the data out over just standard web requests. There's a new logging system, a new common log file. You can get a live feed of packets that it's seeing just over HTTP, and you can do remote capture as if it were local. So, some screenshots of the new UI. It's all web-based and fancy and AJAX-y. And you can view the network details and see graphical representations of the different types of packets and data in them. And you can manage the data sources. You can get graphing of all of the historical data and all sorts of other features you'd expect, in a more modern application. Pardon. So sometimes people try to pitch it as Kismet versus Wireshark, but Kismet and Wireshark are completely complementary. You'll want to use both depending what you're doing. Wireshark is very packet oriented, while Kismet is network and device oriented. So if you're doing traditional packet capture, you're doing analyzing traffic, you'd probably plug into a span port on the network, look at the packets. Maybe you have to worry about VLANs and where packets are divided there. But if you're doing wireless PCAP, you need to worry about what channel is the traffic on. Is it user to user, or is it going through an AP? Are you trying to debug that there's another access point causing interference? Is that keeping you from seeing packets? Did someone bring their own access points from home? Is the problem traffic from an access point you didn't even know was in your office? Are people doing BYOD hotspots where they put their phone into hotspot mode to bypass the corporate restrictions? For Ethernet, basically has one type of packet, which is Ethernet. Wi-Fi has around 45 different subtypes of packets. So Kismet looks at all the contents, just like Wireshark does, to determine the packet types and contents, but then it sorts them into devices, networks, connections, and so on. So the same Wi-Fi device might be talking to multiple networks over the course of several minutes to an hour. So it'll track the interactions between devices. They might be connected to your own access points. They might be connected to fake access points. They might be connected to BYOD stuff that someone brought in from home, and et cetera. And all of that needs to get tracked and related to each other. Kismet can include geolocation from GPS or some protocols that have location info built into them, and it can convert multiple packet types from multiple radios into one record. So if you have 3 different Wi-Fi cards seeing one client, it'll show up as one client instead of 3 different copies of the same packet. So if you look at a packet at a network in Kismet, you'll see signal levels, locations, information about the network that's being advertised, the SSID, various usage patterns, and then clients that it has seen connected to the network, and the time frames that they've been connected and active in. So it's a representation of packets over time. The advertisements and beacons define the network name and encryption. The other information, they can indicate how many clients are connected to the network, and give you other information. 802.11ac and AX information is in the beacons. And the clients are mapped based on their traffic over time, which lets us do trend-based security alerts when these attributes change. The same interaction seen from Wireshark has, you might expect it, where it is multiple packets. So of here we have the same networks advertising themselves over and over again. Some data packets in there, but there's no immediate way to visualize the relationship between the packets and what devices they represent and how they're interconnected, which is where Kismet makes more sense for some views. So you can get all the same info and even more info from each packet in Wireshark, but it's presented really differently. So Wireshark is really good for detailed packet analysis, which Kismet isn't really designed to do. Kismet's meant more for representing the devices that are out there and then letting you drill in and get the packets to analyze. So like we said, Ethernet has one fundamental packet type, Ethernet, and it contains data. And that data might be IP or TCP, UDP, or various things, but it's all Ethernet packets. Wi-Fi has 3 primary packet types and something around 45 sub-packet types under those. So there's management packets that define the network, so beacons. They advertise the network name, encryption options, and things like that. Control access. Management packets also control access to the network, so probes and responses that a client probes to be allowed into a network. The access point responds that it's allowed to connect. And all of these packets can contain nested lists of complex data, which contain all the information about the network or how the client is attempting to connect and what attributes it's looking for. There's also control packets. They're typically very short. Often they only have 1 MAC address in them. They're used for collision avoidance. They're used to say, I'm going to transmit a big packet. Nobody else talk on this channel. They're used to confirm that data was received correctly. And then finally, data packets look like essentially the traditional Ethernet frames. So they can be L2 encrypted with WPA. They could be L3 encrypted, so if it's a VPN or an SSL or whatnot. They could be both encrypted with WPA and running a VPN. So to figure out what's going on with the network, we need all of these packets combined. If you don't have management packets, you won't know what networks are present. You won't know, clients are trying to join networks. You won't be able to see hidden networks. If you don't have the control packets, you won't be able to see hidden nodes. You won't be able to see some denial of service attacks. You won't be able to see, problems where clients aren't able to reserve time on the channel, et cetera. And without the data packets, you'll have no content to see what's happening. Now, we've mentioned channels a few times. You can see all of the channels some of the time, or some of the channels all of the time, but you can't see all of the channels all of the time, as P.T. Barnum famously said. But of course, don't trust every quote you read on the internet. So Wi-Fi breaks up the available radio space into channels. Sometimes the channels overlap, sometimes they don't. On 2.4 gigahertz Wi-Fi, depending on the standard, some are 22 megahertz wide and some are 20 wide, but they're only 5 megahertz apart, which means each channel has significant overlap into the channels that are next to it. So if you're sniffing on channel 6, you could easily see packets on channel 3 and sometimes even from channel 1, which is why when you're doing a network deploy, typically channels 1, 6, and 11 are the only channels considered to be non-overlapping, if you've ever seen that when setting up networks. This gets even worse when you introduce wide channels for 802.11n. But on 5 gigahertz Wi-Fi, there's many, many more channels. There's also 40 megahertz channels and 80 megahertz and 160 megahertz. So this is a challenge because the Wi-Fi radio is designed at a fundamental level to tune to a single channel and be able to very strongly exclude other channels. You don't want other frequencies bleeding into your signal because that will mess up your ability to see the packets. So you need very strong filters on that, but that means you won't see adjacent channels typically. Often they can only tune to one mode. So if you're looking at a 20 megahertz channel, you won't see packets on a network that uses 40 megahertz or 80 megahertz. And unfortunately, if you're tuned to an 80 megahertz channel, you won't see all the 20 megahertz channels within that range, just because of the way the firmware is written typically. If we want to see what's happening across all of the available Wi-Fi in an area, we need to have many radios or we need to change those channels quickly. So it's a trade-off. You can either see a little of every channel, a lot of a few channels, or most of a single channel. Like I said, you can never capture all of the data on a channel, but you can see most of it if you don't hop at all. So this is like trying to listen to all the songs that are on the radio by leaving your stereo in seek mode. You'll hear, 3 seconds of a song at a go, but you won't ever hear the whole song. And more channels means less time spent on each channel or more hardware running at the same time. So we have, 802.11b has channels 1 through 11, and G has 1 through 11. Some parts of the world have, 12 and 14. So we've got, 13 channels or so to worry about with a lot of overlap. It's pretty easy to cover all of these. Then 802.11a came along. So now we've got 38 more channels. And if you notice the gaps in the numbers, it goes, 36, 40, 44, 48. They're further apart, which means they don't overlap with each other. It's much better for signal. This is why, 11A networks and 5 gigahertz, one of the reasons is that it performs better is they don't overlap as much or at all in some cases. Better for signal, worse for sniffing. Now we have 4 times the number of channels we need to look at. Then we have a 802.11n. Well, that's a lot more channels right there. Yeah. So how did we get to 64 channels there? That's because 802.11n added 40 megahertz channels. And you can have a 40 megahertz channel where the extended channel stretches above or below the traditional channel that you're already on. So now you need to look at channel 1, but also channel 1 extended upwards to HT40 plus. You can look at channel 6, but also channel 6 extended downwards and upwards. So now there's 4 channels where before there were only 2. Now we have 802.11ac. Oh boy. So we have 20, 40, 80, and 160 megahertz channels. And on newer 802.11ac, we even have a mode called 80 plus 80, which means 160 megahertz that aren't all in a row. So now there's even more permutations. And within each of those larger channels, they can have multiple control channels within, which means we then have to look at, 4 different control channels within 180 megahertz channel. So suddenly one channel becomes, 7 that we have to tune to. And earlier this year, they just added more Wi-Fi spectrum. There's not much public hardware that supports it yet, probably not until about next year, but they added another 1.2 gigahertz of spectrum. That's more than all of the 2.4 and 5.8 spectrum that's currently available combined. So it's probably going to be a combination of many very large channels for very high bandwidth future protocols and many smaller channels. So the number of possible channels to tune to cover all the available Wi-Fi spectrum is going to explode once this goes more commonly available. And there's even more to add into this. 802.11 AX adds subchannels where it will take a channel and split it and give each user of the AP a smaller piece of the bandwidth, so they can have less total speed but more consistent normal speed for video streaming or VoIP or things like that. So it'll be great for Netflix and Zoom, but much harder to sniff. And there's devices that do non-standard modes. Atheros defined 10 megahertz and 5 megahertz channel widths as well. So now we have 4 channels for every possible original allocation. That if you want to cover every potential method of Wi-Fi, you need to look at them as well. So we need to change channel, and we need to change it quickly to see what's going on. We have 2 choices. We can either hop faster, but at some point there's a limit. Either you're going to be on a channel for less time than it takes for a packet to be transmitted, or more likely the operating system is just going to give up and not set channels that quickly. Or we need to add more radios, which adds It adds more demand for power if you're running off battery. It adds more cost. It adds more antennas. It adds more physical space, and it adds more conflicts in the operating system. Where if you suddenly have 10 cards trying to do things at once, the operating system might not take too kindly to that. But you can add a lot of Wi-Fi cards at once if you really want to. So Kismet's designed to handle this. It can run as many network cards as your operating system can handle. And if you use the remote capture built into Kismet, then you can run many, many, many more. The practical limits are after about 4 cards on one system, the kernel tends to have a bad time. Typically because changing channels on a Wi-Fi card takes a much longer time than most other operations. So if you're hopping on multiple cards, they're going to start, each one is going to start trying to lock the Wi-Fi system, the USB system, the networking system, and then also deal with interrupts for sending complex commands to change the channel, which means that after about 4, you start getting funky results, cards start timing out, the kernel might crash completely. With remote sensors, since you can effectively do 4 radios per sensor and send them over Ethernet, you've got a significantly higher limit for the number of devices you can sniff with on one Kismet session. You'll still be constrained by the CPU and RAM of the system processing the packets. I wouldn't recommend trying to send 12 Wi-Fi cards worth of data to a Raspberry Pi. But if you send it to a MacBook or a other laptop, then you'd have pretty good results. So one of the things Kismet tries to do is it optimizes the channel hopping. So we don't want to hop from one adjacent channel to another, especially on 2.4, but just in general. So it will scramble the channel so that it always hops at least the overlap distance apart between them. So if you have one card hopping through channels 1 through 11, it won't go 1, 2, 3, 4, 5. It'll go 1, 6, 11, 2, 7, 9, or something like that, so that the overlap will help get more coverage out of it. Kismet will also take the channel list and split it between the cards, so that if you have 3 cards with the same supported channels, instead of them all looking at the same channel at the same time in lockstep, it'll split it apart so they'll look a third of the channel range apart from each other. So again, maximizing how much spectrum you can cover at a time as best as possible. So there's some crazy capture setups out there. The Wi-Fi Cactus was demoed at DEF CON. It is 25 Hack5 Pineapple Tetras. So each of them has 2 802.11 ABGN cards. So it's 50 radios capturing packets at once, all sent to a Intel NUC. And he reported that he was seeing over 500,000 devices in a single session of Kismet at DEF CON. And he was filling a 2 terabyte SSD every 2 hours with packets. And he had to lug around a lead acid car battery to power all of that. So this is the Wi-Fi Pineapple. And each of these is a Pineapple Tetra with 2 radios, so 4 antennas per. There's also a company, Alftel, who makes very interesting radios. So they make Thunderbolt chassis with PCI expanders and antenna combiners. So this is probably about $10,000 worth of radios in this tower here. And it is 64 802.11ax radios on one Thunderbolt 3 chain, all feeding into one Kismet instance. So they're able to cover 64 of the 190 channels simultaneously. This is also my own mobile monitoring system in my truck, where it's an Intel NUC and some antennas on the radio, just for data gathering. You can also stick a bunch of different radios in a portable rack, which is what I did for demo. So this is a bunch of 802.11, some custom radio stuff, and some Bluetooth capture. Kismet will also scale down to be super portable. So this is an Intel Compute Stick. It's sort of meant to be a roll your own Chromecast. So it's pulling 3 watts, but that's a quad-core Intel processor with I think half a terabyte of storage in it. And people have also made some setups that are much less portable, I'd say, charitably. This is one of the Wi-Fi Village guys that takes it to various HackerCons and their setup. So yeah, Kismet will run on anything from a single core OpenWRT system with 256 meg of RAM up to however much resources you have to throw at it. I know people who've thrown, i9s with 64 gig of RAM, just because they want to have very large single sessions. As a rule of thumb, you could expect, about 25 to 40,000 devices per session per gig of RAM, and more CPU always helps. But these limits, per running session. So if you want to run it on something like a Raspberry Pi 4 with much less resources, you could just script it to automatically restart itself every hour, and you'll get a new log file and stay well within your CPU and RAM budget. Kismet also has device and log timeout options, so you can have a long-running sensor that doesn't keep everything in RAM. So you can query it and see what's going on, and then it will automatically purge that backlog over time. So you might have seen a bunch of different antennas on the setups there. What antenna you pick matters. You need to pick the antenna based on what you want to do. There's a lot of bad marketing out there for antennas. There's a lot of cards on Amazon that they go, oh, have this 2-foot tall antenna, which is almost certainly not what you want. There's always a trade-off because antennas don't add power; they can only shape it. So you can't get more signal. You can just get more signal in a certain direction. So antennas come in two basic types. There's omnidirectional, which is, the antenna is effective in all directions, hence omni, or directional, where it's most effective in a single direction. And typically, if an antenna is being called directional, then it is usually, 180 degrees down to even just a few degrees of sensitivity in a specific orientation. So if you're going to build a system with your own antennas, you want to learn to read antenna charts. All reputable antennas should have a chart provided that show their power in their advertising material. Typically, the chart is just, it's shown as a horizontal and vertical gain. It could be labeled horizontal and vertical, or elevation and azimuth, or just X, Y, and Z. So for example, here's what the graphs of a highly directional antenna would look like, where you can see that on the back of the antenna, there's almost no signal. And it's all concentrated in effectively one direction, both in the horizontal and vertical. So if you took that same plot and looked at it in 3D, it would look something like this, where behind the antenna there's almost no signal, and then the greatest concentration is in front of it. So physically, an antenna like that might look like this, kind of like the old TV aerials. They're called Yagis. They're also called, sector antennas, or other things have similar characteristics. You might see antennas that look like this. That's effectively the same mechanical antenna inside, and you would have a similar effective pattern. So you wouldn't want to use this if you were looking for all the Wi-Fi in an office building, because this would completely exclude anything that's behind you. But it would be great if you're looking to monitor something far away, or use it to find what direction something is in, because it limits it to only see in that direction. Versus an omnidirectional antenna, where a similar plot, but looks extremely different, where the horizontal coverage is almost 360 degrees equal, and the vertical coverage is also very, very widespread, with a couple of interesting characteristics, because this type of antenna basically looks like a donut, where right on top of it is the least gain, but then spreading out from it like a donut or an apple shape is the most effective radiation pattern. And this would be what you typically find on, your access point at home or in your laptop, embedded inside the LCD panel, because you want the most wide coverage possible. You don't want it to limit what direction that goes in, because people will put the access point wherever they feel like in their house. So in 3D, it looks kind of like a torus or a donut, where it has great coverage in all directions except directly above and below. So they look like this. But remember, more gain isn't always better. More gain, some people say, that's what I need, but not always. So the trap that people might fall into is, the marketing on Amazon and other sites, where they go, here, have this 18 dB gain antenna, which is ridiculous. So, it's a silly level of gain. So we look at those same graphs again. Before, the vertical was almost the entire range. As you increase the gain, the donut gets flatter and flatter and looks more like a disc or frisbee, which means it's less and less effective above and below where it's oriented. This could be as low as a few feet or less of vertical range. I've seen crazy high gain omnidirectional antennas where if you were, if it was on a table and your laptop was on the floor, it could not see that network at all. Or even just if the access point was up on a shelf versus where your antenna was, you wouldn't see it. So randomly increasing gain isn't going to necessarily help you in most cases, which is, again, why access points and that stuff come with much more modest antennas, 2 dB or 5 dB gain instead of 18. Also, if you're taking your own antenna, if you're doing it for Wi-Fi, you need an antenna designed for Wi-Fi. It needs to be 2.4 and 5.8 gigahertz. It needs to be 50 ohm, and it needs to have the proper connectors. Any antenna you buy labeled for Wi-Fi will meet these characteristics. However, if you have older antennas for CB or TV or ham radio that are not what you want, even if you could get the connectors to fit, it won't perform well and could even damage your radio. So just make sure the antenna you're getting is designed for what you're using it for. So we've talked exclusively about Wi-Fi now, but Kismet can do more than just Wi-Fi, and there's a lot of other interesting things out there in the airways. So if you want to capture them, you need either a radio specifically designed for that protocol. So if you want to capture Bluetooth, you probably need a Bluetooth radio, or you need a software-defined radio and appropriate software to run it. So Kismet can handle non-Wi-Fi data now. It can handle other radio packet protocols. It can handle stuff that isn't strictly packets. So there's a lot of things out there that don't have a real standard because they're just, what a company used to make a wireless light switch or something. It's really hard to get a PCAP definition when it's essentially a manufacturer one-off, but with the right hardware and software, you can still decode the packets. So for SDR, software-defined radio. So if you have, traditional commercial radios, Wi-Fi or Bluetooth or whatnot, they're designed for one thing. They don't take a lot of power to run. They don't take a lot of processing power to run because it's all built into the chip. They have dedicated chips that can do Wi-Fi. So you have a chip in your Wi-Fi card that is the chip that talks Wi-Fi, but it's only able to talk Wi-Fi. It can't, your Wi-Fi chip can't handle the Bluetooth protocol even though it's on the same radio band. And it certainly can't handle something on a different radio band. So a software-defined radio is a generic radio digitizer and RF front end. So it can handle, air quotes, any protocol if there's software for it. The catch is it's very power hungry. It's incredibly CPU hungry. They are very expensive usually compared to a, mass-produced Wi-Fi card. The radio usually isn't as good because it's seeing much more than just Wi-Fi. So if you had an SDR that could cover Wi-Fi and a gigahertz in either direction, then it's not going to be as discriminating as something that's got very strong filters that can only see the single Wi-Fi channels. Also, software for SDRs is quite hard to write. And a lot of it that's out there is something I jokingly call gradware because someone wrote it for their grad student project and then graduated. And now it's still out there. It's like, oh, well, you can maybe use it, but it probably won't work with anything modern. Different SDR hardware has different features. So if you're looking at it, you'll typically see, the bandwidth, which indicates the amount of data it can capture at once. So, Wi-Fi is 20 megahertz wide. Most SDRs top out around there. So you can see theoretically traditional Wi-Fi channels, but you would need a much more powerful SDR to see 802.11n at 40 megahertz wide. And forget about, 11AC at 160. You can also buy SDRs based on the range, the amount of spectrum it can cover. So it could do, 300 megahertz to 3 gigahertz, which would cover a bunch of interesting industrial networks, and then lower Wi-Fi 2.4, but not 802.11ac at 5 gigahertz. So typically the more range it covers, the more money it will cost, and the more resources you need to cover that range. There's also the sample size. The cheaper ones report in 8-bit, the more expensive ones report in 16-bit. Typically, this is less of a concern because you'll be buying based on bandwidth and range rather than sample size. Some of the more advanced ones have multiple radios operating in MIMO, whereas the more cheap ones have just a single radio, so you won't be able to do MIMO reception. And as you add more features, of course, you add a lot of money. It's very easy to add up to thousands or tens of thousands of dollars worth of SDR radio. But it's not all doom and gloom. There is at least one cheap as dirt SDR option. It's called the RTL SDR. It's designed off a tuner meant to receive European DVB terrestrial TV. It can still receive TV, but people figured out how to hack it to return raw radio samples. So it's not a very good SDR, but it is a very, very cheap SDR. It's limited on as to what spectrum it can see because it's designed to receive these TV signals that aren't up in 2.4 gigahertz. So you can't see things like Wi-Fi or Bluetooth with it, but you can see a lot of other things. How cheap is it? One of the better, more reputable, more expensive models is $29. So, and you can get them even cheaper, but I would recommend, around $30, you'll get a decent one. It is a crap device, but for $20, a crap device goes a long way. It is a great way to get into SDR. It's a challenging field. It can be tricky to set up, but it can be really fun to detect networks or other devices that aren't Wi-Fi and whatnot, or learn how to write decoders for radio protocols. So this is a good way to get your feet wet in that and see if you want to pursue it further or if it's just too complex and flaky to be interesting. Kismet can use it for a number of things, or you can use a bunch of them at once for multiple protocols. So some of the protocols we can capture with a $30 RTL SDR is power meters. Some implement power monitoring so that the power company can read them from the street. Kismet can also decode them. So here's 2 power meters near my house, and I can watch my power consumption tick up. Weather and temperature can be received by them. A lot of weather stations use 433 megahertz, which is another public band, to link to the display inside the house. Same for the wireless thermometers, where you have 4 thermometers you distribute around your house and 1 panel that shows all the readings. So we can pick those up and see them. So thermometers like this. So for $10, you can throw thermometers all around your house and then watch them all from one location and log them with Kismet and pull the data. So we can see, temperature and humidity pulled off of them. There's a protocol called ADS-B. The FAA now mandates that planes have an active transponder that sends their registration info, the call signs, altitude, direction. This is how sites like FlightAware work. They have this huge monitoring network of people who monitor these signals and automatically contribute them to the database. So Kismet can pull these out too, where we can see, airplanes flying by, which is pretty fun. So you can plot, airplanes that are near you, what direction they're headed, their altitude, and all of that. I think the best one I've seen is one of NASA's private jets flew by. So the signals coming out of the SDR is, too complex to go into in any great detail, but it's called IQ data, which is the power and the phase of the data, which can be used to decode the radio signal. It's really complex to identify packets among the noise, and this usually takes a lot of CPU. Typically, any SDR thing you're going to do is going to use 100% CPU. So just plan for that. So Kismet can also detect Bluetooth. It's much harder to sniff than Wi-Fi because it does frequency hopping, and there's not that many devices that can give you raw packets. But Kismet can detect advertising devices with just the Linux HCI drivers, so just standard Bluetooth and Linux. There's also a bunch of cheap USB devices that can capture Bluetooth packets, and you can get the BTLE advertisements and get actual raw packets that way. So you can see, nearby Bluetooth. So for example, there's a bunch of tile sensors. Those, I lost my keys, find it with my phone thing, along with people's phones, and it looks like either a Bose headset or a stereo or various things like that. So we can detect all of that at the same time as we're detecting Wi-Fi. There's also a protocol called Zigbee, which is a industrial control protocol for the most part. It's also used for some home automation stuff. With the right hardware, Kismet can capture that. You can get USB cards as cheap as $15 that can see that. Currently, the part of Kismet to display those packets as networks isn't available, but you can log it to PCAP and look at them in Wireshark. Some wireless keyboards can be sniffed and detected. Logitech, Microsoft, and whatnot use a chipset called the NRF or Nordic RF, where it's a little dedicated radio that isn't Bluetooth or anything like that. It's the keyboards that come with those little USB dongles that you have to plug in. Those can be sniffed. So if you have again a cheap USB device that has the right stuff, Kismet can detect keyboards that are near you. So given all this data we collect, we can detect different shenanigans going on near us. IDS is intrusion detection system. WIDS was a wireless intrusion detection system because we're creative at naming things. So Kismet can detect attacks, it can detect denial of service, it can detect other weirdness going on. It doesn't attempt to prevent it. It's not a intrusion prevention system. Often that's not even possible. Someone can be messing with you and there's just nothing you can do about it, but knowing that it's happening is valuable. So Wi-Fi presents a very large attack surface. The packets are complex, the data in them is complex, they have weird nested cascading data structures that are easy to get wrong. Also, because anything transmitting near you affects you, it's really easy to cause a denial of service, either just by jamming the spectrum or by transmitting packets to say, this channel's busy, this channel's busy, this channel's busy, and then the network never has a chance to do anything. It's also easy to do spoofing or impersonation, and there's been a number of attacks against various Wi-Fi drivers. So in the Kismet WIDS, there's three main types of alerts. There's trend-based alerts. So traffic that's otherwise normal, but taken over time indicates something is strange or broken. So like a denial of service attack that says, disconnect all the users from this network. That's totally normal to happen once, but if it happens 100 times in a minute, that's a denial of service attack, raise an alert. Kismet also has signature-based alerts where there's specific bad packets. Some of them are, buffer overflows in drivers or other malformed packets that are designed to cause problems. And those are easy to spot because those are never legitimate. So it's just, as soon as you see this, that's an alert. And also you can do user configured fingerprints where you can set up regular expressions and whatnot to match similar networks or to look for specific MAC addresses and whatnot entering or leaving the area. So some example detections Kismet offers. One of the trend-based ones is encryption options changing on a known access point. So, we said devices are tracked over time. So the access point, we know what it used to advertise. We used to advertise WPA, and now all of a sudden, something claiming to be the same access point is advertising no encryption. That's almost certainly a problem. You could also write a regex to find network names similar to the official one. So if you have, the official one is called my network, and you can detect, my network underscore, someone trying to spoof to get people to connect to the wrong network at a conference. We can also detect brute force attempts against WEP and WPS and whatnot because they are fairly intrusive and transmit a lot of packets. So, the more data we have, the more discrepancies we can find in it. And we can look at other vendor-specific flags because often attackers don't completely duplicate a network properly. Also, just announced yesterday, there's a new attack against Bluetooth called Bleeding Tooth. And the Git version of Kismet now has detections for that. So if you have the Bluetooth BTLE sniffing hardware, you can detect that. I'm going to go through the last of this really quickly before Q&A. So get your questions ready. No tools island though. Kismet has APIs to talk to other tools. You can convert the log files for other tools. Old Kismet had a custom TCP protocol that nobody used. The new one just talks HTTP and JSON. Any language that can talk HTTP and JSON, Ruby, Python, JavaScript, Node.js, and whatnot can all talk to Kismet trivially. Everything has a REST-like API, and it's all heavily documented on the website. You can also stream PCAP over HTTP. You can also filter by device or access point or capture card live in the PCAP stream before you hand it off to another tool, and you can filter packets from the log file. You can also run Kismet through Nginx or another proxy. You can add SSL via Let's Encrypt. You can tunnel it over SSH. You can do remote cap over SSH, etc. The new logs are much easier to handle. Instead of multiple files, it's all combined into one with the packets, the reports, the device information, configuration info, alerts are all in one log now. You can convert those to PCAP or PCAP-NG, CSV, JSON, any language that can talk SQLite and JSON can do complex filtering and extraction of data from the logs. And now that the log is a database, it's random accessible. So we can do things like ask the Kismet server to give us all the packets that occurred 5 minutes before and after an alert. So now we can see, okay, this WIDS alert triggered, what happened? You can also extend Kismet with plugins. You can have native code. You can have external code written in Python or Ruby or whatnot that talks to it over IPC. Or you can have web-only plugins that define new interfaces. Here's a whole custom mobile web UI based on just a plugin that defines new HTML and JavaScript for the web UI. Coming up is going to be more WIDS features, WebSockets for simpler remote capture and a better UI interface, and handling packets from more types of data. And you can find Kismet at kismetwireless.net. That has links to the packages. Kismet has its own Discord. All the documentation is there. And Kismet Wireless on Twitter for release information. I'll post there when new releases come out or new features get added. And since there's no questions yet, here's just a quick example of, here's a Kismet server running with all sorts of different devices. We can filter by, here's all the no, of course we can't. The curse of the demo gods. In any case.
While you sacrifice a lamb to the demo gods, you do actually have 3 new questions.
Oh, here we go. So Robert asks, is there a tool that can take Kismet data and create a relational map to show what clients are connected? Not yet, but there is an API that gives you all of those relationships in a JSON record. And I started using one of the JavaScript-based graphing tools to do that in a browser, but it's not quite done. Isaac asks, who makes the 64 radio one? That's Alftel, ALFTEL. I believe they sell it as a handful of like you don't get all 64 at once, but it's a set of expansion boards that can be daisy chained. Kismet name came about because I was I think I put NetStumbler had just come out, and I think I put stumble into thesaurus.com and clicked at it randomly until I hit a word that wasn't another open source project that sounded cool. No great story there.
That is a great story.
Stefan asks, why isn't the same as on FlightAware? Because FlightAware is based off hundreds of people with antennas all looking for planes and combining them, whereas any given single antenna is not going to see all of them, either because they have better radios that are more discriminating and can see more packets, or because they're at a higher altitude or similar. That said, my antenna is inside my attic of my barn, and I can see planes that's about 300 miles away. So even fairly cheap gear, and mine's mounted indoors because I don't want to deal with lightning hitting it by mounting it on a big tower outside, can still see, a lot of planes far away. The problem with this is that it's easier to see planes that are 30,000 feet up, hundreds of miles away, than it is to see, helicopters and planes closer to you that might be below the range of a local hill or trees or whatnot. But if you had multiple sensors distributed around connected to one Kismet server, you'd be able to see more planes. As a test, a friend down in Philly has been running a server as well, and we've combined the two of them so that we can get coverage across this whole range, which is kind of fun to watch. David asks about WLAN Pi. I believe I've met them, but I'm not affiliated with them. So I'm not sure if they have plans to integrate it or not. I believe the guy who does that has been through the Discord channel a few times and we've chatted, so he might be working on adding support. And now things are cooperating. So here we can see, a bunch of different nearby devices. So, here's a weather station that's near me, so I can see, the wind direction and humidity, and that I need to replace the battery in it. And all that's coming off of one of those super cheap RTL SDRs. And then we have, Bluetooth devices that are near me. BTLE supports random MAC addresses, so there's often a lot of junk in here that sends, a few packets and then changes the randomization. But these are things like Nest smoke alarms, so you can, see things like that. Here's all the planes appearing off one of my sensors. And I mentioned how Kismet can do transparent remote capture. So of these, some of these are on my local server and some of them are remote. So, this is a USB device plugged into my local server, whereas this is a Raspberry Pi 3 in the attic doing remote capture of ADSB. So it's up high where it can see more planes. Robert asks, quick overview of WID setup. So by default, the alerts are all turned on. There's a page in the documentation that explains each of the alert types, but they show up here as alerts in this in the interface here. Unfortunately, I don't have any interesting ones here, but those show up in this, and then there's web-based APIs that you can use to pull alerts based on time and either of all time or recently. They're also logged into the log file, and there are some example plugins to take them and send them to syslog. There's also some optional code that can integrate it with Prelude monitoring engine, and then anything that can take syslog can be easily integrated in. Someone's asking, running on Mac OS. Yes, there's directions on the website. There is no package because of Apple's code signing requirements, but you just need to install Xcode and a couple of other utilities, and it will compile and build and run there the same as it does in Linux. There's a few quirks to compiling the latest release. I just replaced the entire core web server code to make it work better on Mac OS because the HTTP library I used stopped working on OS X correctly. But yeah, all the instructions are on the webpage. I can link it in Discord after the talk as well. Isaac asks, how does it merge the captures from different PCAPs? It works on fingerprinting the contents of the packet, so it will basically do a quick checksum of the non-variable parts of the packet. So it'll exclude the radio headers with the signal levels and just take the contents, either the beacon contents or the data contents, and do a quick checksum. And you can configure how many packets back that looks. I think by default it keeps the last 2,000 packet hashes. So it just does a quick checksum and hashes back and looks for that and figures out if they are the same packet seen from multiple cards in the same time period. I don't know if there's any other questions.
So you already answered merging the captures from separate PCAPs? Got it.
Yep.
Yeah, I was just going to say, why don't you go ahead and show the link to the survey?
Yeah, I was trying to. It lost my mouse.
Understood.
So yeah, if everybody has time to fill out the speaker survey, that really helps. And I think we have a few more minutes for questions if anyone has any, or if I can show anything specific in the UI, happy to do that. And I'll be on the Discord after this for the if there's any questions people wanted to ask in that format instead. And if anybody wants to remind me of links I said I'd paste in that section, in that format, I'll paste them over into Discord.
So Jesse just asked if there was any recommended tutorials or education sources he could learn to integrate this into curriculum in the chat. So.
I mean, I'll make this presentation available if you want to steal anything from it, by all means. There's also a lot of documentation on the Kismet site, both about how to configure, mostly about how to configure things and about the API. Just under the documentation link here. So depending what you want to do in a curriculum. It's certainly possible to just, there's also packages available for Raspberry Pi and whatnot, so you don't have to compile it. So if you install Kali or Raspbian on a Pi, like a Pi 4 or something, then you can just pull the latest versions or even the nightly builds onto it that way. But if you're also looking at doing, like, someone had asked, how does it integrate with for alerts? So for example, here's all the documentation on the API to return alerts. So this, has all the info about, the endpoints and what information comes back from them. And everything in here just comes from JSON. So everything presented in the UI comes from the REST API. So everything the UI does, you can automate or create your own interface for, or extract data for presentations or whatnot. And inside that API, it actually has, every single field has a name, a type, and a description. So you can query the server and get, the raw JSON, or you can get the pretty format where it gives you all of that additional info, or you can directly query. So you can query the system to get a live listing of every field that's supported in the system. So if you're looking at the JSON and trying to integrate it with a tool, you can go in and go, okay, I have, this weird field, what is that? So if it's, it's a 8-bit integer, and that's what it is. So, there's something like 600 fields, but each of them has a type and a description of what it is. So it's a lot easier to write tools to integrate with it. And I think that's about it for time. So unless there's any last minute questions, I will be in Discord. And thanks everyone for joining, and I hope you have a great SharkFest.